Okay, Bismillah Rahman Rahim. We are discussing the topic of stereo and particularly that of epipolar constraint. Okay, um, I've changed the slides a little bit from what we were having last time, mainly in terms of notation. The fonts for I'm using a different font for a vector, a different font for a matrix. That's what we had been using, and they were the slides that I used last time were from my previous lectures. They were not consistent with that, so I've just changed them a little bit for consistency. So they are slightly different in terms of notation. Um, no major difference. It's the same thing. I just want to review what we did last time and then continue on from there. Okay. So we are trying to build a framework for. Okay. We are trying to build a framework for epipolar geometry to understand epipolar geometry, and that includes understanding what is the fundamental matrix and what is the essential matrix. These two matrices are essential to understanding stereo. All right. So what's the geometry here? We have a camera center. I had written that O last time, but it's really the same camera center C that we have been used to. So there's CL and CR. Those two are the camera centers. And then there's a world point P. You are looking at that point from two different coordinate frames. One is the coordinate frame of the left camera. So that's PL, this thing here. And the second is the viewpoint of the second camera, the right camera, and so that's PR. And then you have the two imaging planes, so you have the image at small pl and then small pr. Okay. And then you have the left epipole and the right epipole. Epipole lies along the line joining the two camera centers, okay, because it's the image of the camera center in the other camera. Okay, so that's the notation. PL is XLYLZL, PR is XRYRZR. We did that, and then a small PL is XLYL and really FL, which is the left focal length, and small PR is XRYR and FR. Okay. So with that notation, we saw that we can relate PL and PR, the two representations of the world point, right? We can relate them in the two cameras by the rotation and translation of the second camera with respect to the first camera. Okay, so that's just the relationship that brings them into the same coordinate system. Okay, where this translation is the translation between the camera. We call it the baseline also, CR minus CL, and R is the rotation of the rotation between the cameras. Okay, and then small PR and small PL are related to the capital ones just by the perspective transform, which is FR over Z. I could put a minus sign if I want to. Both conventions are okay. So PR is FRZR over times cap PR, and PL is FLPL times cap PL. Okay, is that fine? No issues. All right. So the fundamental derivation for the essential matrix relies on that diagram that I made, which is really a coplanar triangle, and in fact that's why we say that stereo, we are doing triangulation to get stereo. Okay, so the vector PL, the vector T, this was the geometry, right? So the vector PL, the vector T, so this is T, this is PL, and then T minus PL minus T, which is another vector in the same plane because it's formed by these two as the bases. It's formed by an addition of these two. So that would be PL minus T somewhere here. Okay, all these three vectors are coplanar because the third one is written as a linear combination of the first two, so necessarily they are in the plane of the first two. Okay, because they are coplanar, I can write that fact that they are coplanar like this: PL minus T transpose into T cross PL. T cross PL is normal to this plane because it's formed by the cross product of two vectors on the plane. So T cross PL dot product with PL minus T should be 0 because any vector on the plane should be orthogonal to the normal. Okay, that's a fundamental property of the plane. So that's a way to write the relationship between PL and T. And then since I know that PR is R times PL minus T, that is PR is just a rigid body transform applied on PL. Okay, so I can substitute, instead of PL minus T here, I can substitute R transpose PR. Take R on this side here, so you have R transpose PR transpose T cross PL. Agreed? All right. And now that I have this, I'm going to do one more mathematical trick. I'm going to write this cross multiplication. We did that last time. I can write this as a skew. I can write this as a skew symmetric matrix S. This is a notation. I didn't use that last time, but generally skew symmetric matrices are written with the subscript X in the textbook. We have seen that before. Where did we use a skew symmetric matrix before? Did we? We mentioned skew symmetric matrix somewhere. No? Yeah, in Rodriguez formula you have a skew symmetric matrix n subscript X. Okay, so I use the same subscript there. So I'm writing it like this, where S is nothing but it's composed of those translation terms. It's constructed in a way that you multiply this S with anything, any vector, it will really be the cross product of this T with that. Okay, skew symmetric matrices of odd size always have a rank deficiency of 1. We talked about skew symmetric in one of the tutorials. It's not exactly symmetric. One half of the symmetry about the diagonal is negative of the other side. Okay, and the diagonal itself is 0, so that's called a skew symmetric matrix. And skew symmetric matrices always have a rank deficiency of 1, and I showed you that if you multiply the first column by minus tx over tz and the second column by minus ty over tz and add them up, you'll actually get the third column. So that shows you that the third column is linearly dependent on the first two columns. The first two columns minus the first two columns times a scale factor added together give me the third column. Okay, so since I can write the cross product as a matrix product, so I'm just writing that here as a matrix product. This is the same thing. And now what I'm going to do is I'm just going to expand this transpose out, so it becomes PR transpose E PL, where E is R times SX. Okay, R is a full rank matrix. R is a full rank matrix, but SX is not. SX is rank 2. So R times SX is also rank 2. Okay, and we call this the essential matrix. So that's where we were last time, right? Any questions? So one thing we can do on this is these are now world points. PR and PL are world coordinates, but I can actually transform them into image coordinates because I know what's the relationship between world coordinates and image coordinates. The small PR, which is the image PR, is really equal to the cap PR into F over Z, FR over ZR, right? That's the relationship between world points and image points. So what I can do is I can multiply this equation just by FR over ZR. I can multiply both sides, but the other side is 0, so there's really, I'm multiplying by a constant, so the equation still holds. And I can also multiply it with FL over ZL. Again, the equation does not change because the other side is equality. And then this factor I attach to this vector, and this factor, it's a constant, so I can just multiply here. I attach to this factor, and so I can convert this equation into image coordinates rather than world coordinates. And so PR is FRZR over P times PR, and PL is FLZL times cap PL, and so I get this equation, which is in the image points. Okay, the points in the image, the left image and the right image, are related by this constraint. Okay, where E is something that is composed of R and T, because SX is really formed out of T. So so E is really something which is purely dependent on the extrinsics of the camera. Okay, it's dependent on the relationship between the cameras. What's the geometry between the cameras? You can assume one of the cameras is in the canonical view, so the other camera is at an R and T from that canonical view. uh, if if the relative geometry of the camera you fix it, then E is fixed up to a scale factor, obviously, because this is a projective equation. Okay, what does this really mean? Excuse me, class area, right? What does this really mean? What is the nature of this relationship? Well, think of it like an equation A transpose X is equal to 0, where X is this EPL, because what's the dimension of EPL? Combined E is 3 by 3, PL is 3 by 1, so EPL is a 3 by 1, so it's a vector. So think of it like A transpose X is equal to 0, which is an equation of a line, right? This type of equation is an equation of a line. So the essential matrix gives us the epipolar line. What does that really mean? That if you give me PL or PR, either one of them, if you give me PL, then sorry, I should have written PR here. If you give me PR, then EPL are the coefficients of the line in the second image, and vice versa. Okay. So this statement I just need to correct because I've written PL twice. That's not correct. So if you give me one of them, the other side becomes the, so if you give me PL, then PR transpose E are the coefficients of the line in the other image, in the right image. If you give me PR, then EPL are the coefficients of the line in the second image, because A transpose X is an equation of a line. Okay, so this shows you that this is not a relationship like a homography. In homography, you give me one side, you give me one point, I multiply that by X, I get another point. Okay, so the relationship is like X prime is equal to HX. But this is not a relationship like that. This is a constraint on the point in the other side, and it's a linear constraint, so you actually get a line in the other image. Agreed? All right. So just as an example, think about a simple case where the camera has only translated along the x direction. Okay, so the axes are like this. There's x, there's y, and then the depth axis is z. Okay, and the camera has, so this was the canonical camera. So it's at 0, 0, 0, and then the other one is, there's no rotation, there's only translation along the x direction. Okay, so R is really, in this case, so this is a simple example. The camera just perfectly translates. The imaging planes are aligned. They are parallel to each other. In fact, they are the same plane really. It's the second image plane is just an extension of the first image plane. Okay, in the translation direction. So so what happens here is that R is identity because there has been no rotation. Okay, and T is this vector along the x-axis, 1, 0, 0, or any scale factor of that, depending on how much I translated. Okay, so what would be the form of my essential matrix? How can I see that? Anyone? Sorry? Yes, so you're right that E is equal to RS and then S sub X, and X has that form which had like 0, 0, 0 here, and it has minus TX, TX here, and I think minus TZ here, right? TZ, and then TY and minus TY. Okay, I think that's correct. So so really my TX, my TZ and TYs are 0, and I have minus TX here, and sorry, this should be X because it's skew symmetric. So minus TX and TX here, and TX is really 1, and then TY and TZ are 0. So E has this form. Okay. You can see that this is the rank 2 matrix. This vector and this vector are independent from each other. You can't write them as scale factors of each other. And this vector is purely 0, which results in the rank deficiency. you can always write 0 as a scale factor of any other two vectors, because 0 times that vector plus 0 times this vector. So anytime you have a column of zeros or a row of zeros, a full column or a full row of zeros, that's a rank deficiency. All right? Yeah. Can I explain what again? R is identity, and Sx I just plugged in these values. This is Tx, this is Ty, this is Tz. So I just plug them again, right? And yes, it's satisfying that this is a rank 2 matrix. All right. And also, let me emphasize that this is a rank 2 matrix that depends only on the extrinsic parameters of the camera. All right. Yeah. Where is R? Where is R? What is R? It's the rotation between the two cameras. So it's the same notation that we are using when we describe a camera. We describe it as K R pipe T, which is really K R pipe minus RC, right? So the camera undergoes some translation and rotation. The first camera is at in the canonical view, and the second camera is some rotation and translation from the first camera. All right. Okay. So I just did it as I just did this as an example so that you build some understanding of what is an essential matrix. Okay. Now, here are some properties of the essential matrix. The essential matrix is of rank 2. It can't be of rank 3, and also it's not a valid essential matrix if it's rank 1 or all zeros. It provides us a way to find the epipolar line, because if P1 transpose E P2 is equal to 0. So you plug in one point, you get the line in the other image. So it provides us a way to find the epipolar line. And it codes the information on only extrinsic parameters. It depends only on R and T and not on anything else. And now note that PR transpose EPL requires us to know the image points in real world coordinates, not in pixel coordinates. This is a bit of a problem with the essential matrix, right? Why is that? By real world coordinates, I mean centimeters. Yani the image pixels should be known in meters or centimeters rather than in pixel value 100, 200. Why is that? Yeah, exactly. Because we got this P by simply multiplication of F over Z times the world coordinates. So the unit remains the same. I have not done a unit conversion. Okay. So the essential matrix does relate a point in an image, in one of the image, to a line in the second image, except that this relationship is in real world coordinates. Okay. So that means, because I'm talking about real world coordinates, that means that the camera intrinsic parameters have to be known to be able to use this equation, right? Because if I ask you a pixel value, I pick a pixel and I say this pixel is 100, 100, and then I say apply this equation, you can't just use that 100, 100 value in this. What you will have to do is you'll have to scale it by the width of the, remember those mx and my factors? You'll have to scale it by the width of the CCD array to convert it into pixels. How many meters per pixel are there in that dimension and this dimension? You'll have to do that conversion, and you'll also have to do the conversion if the image axis, the origin of the image axis was not at the principal point. You'll also have to do that conversion of the principal point, which typically it is not. Typically image origin is at the corner of the image rather than at the principal point in this close to the center, right? So you'll also have to do that conversion to be able to convert that meters value into pixel values, okay? Or the other way around, actually. I'm giving you pixels, so to be able to convert those pixel value, you'll first have to convert that into meters value for that pixel, and once you have done that, you can apply this equation. All right. Okay, now having said that, oops, a bit of problem with my, yes, go ahead. Yeah, we'll just do that now. Okay, so there is this other matrix which is called the fundamental matrix. The mapping between the epipolar lines and the points can be obtained even without knowing the camera parameters. Okay, so let's see how. So we'll extend this mapping a little bit. So you know that this is the epipolar constraint, except it's the epipolar constraint in the real world coordinates. Okay, now I can actually convert them to pixel coordinates, and that's just a matrix multiplication containing only intrinsic parameters. Let me call that ML and MR. Okay, what does ML contain? It should really have MX and MY and then X0 Y0. I mean, it should be something like that, remember, right? To be able to do the appropriate scaling and the appropriate translation. Both are scalings and translations in 2 dimensions. These are P2 matrices. Okay, so I can have this intrinsic kind of matrix of the left image and in the intrinsic type of matrix of the right image, and I do that scaling and translation, and I get it into pixel coordinates. So I'm writing pixel coordinates by a bar here, just to distinguish them from the real world coordinates. Okay, so you feel comfortable, you can do that, right? How would you do it? You'll just take this value in centimeters and then multiply that with pixels per centimeter value of that camera CCD array. You'll have to find that from the camera specifications, and similarly for the other dimension, and then you will adjust for the origin, because the origin for the original equation in the real world coordinates was supposed to be at the principal point, and now it's at an offset from the principal point, so you'll just add that offset. Okay, and so I'm going to do this substitution back here into this equation. Instead of PR, I will write instead of PR, I will invert this here, and I'll write MR inverse PR bar, and then so on, right? So I just write this in pixel coordinates now, and this in pixel coordinates, and this equality must also be 0, because it's really a substitution into this. Okay, but now my PR bar and PL bar are in image coordinates, which is more convenient, because that's what if I click something on the image, I get it in image coordinates rather than in real world coordinates. Okay, so this is what we have. This is what I had from the previous slide. What I can do is I can take this transpose and open this up. A times B transpose is B transpose A transpose. So I get PR transpose MR minus transpose, which is the transpose of the inverse, into E into ML inverse PL bar equal to 0. Okay, and now consider this thing. E is a 3 by 3 matrix. ML inverse is also a 3 by 3 matrix. MR minus inverse transpose is also a 3 by 3 matrix. And so let me call that 3 by 3 matrix F. Okay, and that's called the fundamental matrix. If I define this as F, then this equation simply becomes this, right? PR bar transpose F PL equal to 0, which is awfully like the essential matrix equation, except this equation is now in pixel coordinates. In fact, consider F. E was a rank deficient matrix. MR and ML both are full rank matrix because the diagonal is complete. So both are full rank matrices, and none of the columns can be written as a scale factor of the other two. So I have a full rank matrix times a rank deficient by 1 and times a full rank matrix. So the rank of F is also 2. Okay, so F and E are actually related by this equation, and they're both of rank 2. And now what can I do with this equation? So this tells me that you are given 2 images. You pick a pixel in the first image in pixel coordinates, which is easy to pick. Okay, and then through this relationship you will get the line in the second image that this pixel must correspond somewhere along that line. All right, any question? Yeah, please louder. No. uh, Let me give you an example. Let's say f, there's some f here, right? And this part is given, the left point is given. Let's say the left point is like 100, 101, okay, and the right point is not given, so I'll write the right point as x, y, 1, okay, and then I write that equal to 0. So this times this gives you three values, right? Let's say 2, 5, 3. So then your equation just becomes 2x plus 3y plus 5y plus 3 is equal to 0, which is an equation of a line. So there's no like null space or anything here. It's just that you plug in one of them, you'll get the line in the other image. Okay, yeah. What? Yeah, okay. So I'm saying, yeah, the last point here, the equation is now in pixel coordinate. And so to be able to apply this equation, I don't need to know camera parameters. All I need to know is corresponding points to find f, or if I have f, I can find the equation of a line. Everything is working in pixel coordinates. Previously, that was not the case. I will pick a pixel coordinate. I will need to know the camera intrinsic parameters to convert it into real world coordinates and then use this relationship. But now I can just work in the pixel space. I really all the camera parameters, both the extrinsic and the intrinsic parameters, are embedded within f. So if somebody gives me f, I don't need to do any more effort on the camera parameters. Is that clear? Yeah. And now we will see, the reason I'm saying I don't need camera parameters is that now we will see that if you give me a bunch of correspondences, I can actually directly estimate f. I don't need to do a calibration procedure. I can directly estimate f. Okay. Yeah. Yeah. That's actually correct. Because we'll see in the next module that we have a bunch of methods to find correspondences. So what I can do is, the way stereo algorithm works. So you have a good point, but I said this yesterday also, and I'll summarize again. The way stereo algorithms work, you first find a few correspondences. Now, based on the few correspondences, you actually find f. Now, based on f, now you can find many more correspondences because now you have a constraint on those correspondences. So first, in the first step, you find sparse correspondences. From sparse correspondences, you find f. From f, you find dense correspondences, which means correspondences really for every pixel or almost every pixel. And then those correspondences really are disparity if you have done the rectification properly. And so that disparity can then be converted into depth if the camera extrinsic parameters are known. The extrinsic and intrinsic parameters are known. Okay, so there's really a whole procedure to this theory. All right. So, like I described some of the properties of the essential matrix, here's an equivalent slide for the fundamental matrix. The fundamental matrix is also of rank 2. No surprise here. It gives me a way to find the epipolar line in pixel coordinates now, actually. And the essential matrix encoded only information on camera extrinsics, but the fundamental matrix encodes information on both extrinsic and intrinsic parameters. Okay, because it was really the essential matrix which was extrinsic, and then there are two matrices multiplied on either side which are the intrinsic values. It contains the intrinsic parameters of the left and the right camera. Now, if f is known, then there is no additional camera parameter information required to find the epipolar lines. Okay. One point that I want to make here, which is how many degrees of freedom in f or in E? 8. Oh, okay, so that's a good point. F has 9 terms, but since this is a homogeneous equation, the scale factor doesn't matter. An f and a scale factor of f really both are the same fundamental matrices. So really one freedom goes away because of that, and so there should be 8 degrees of freedom. Yeah? 6? Why 6? Okay, your argument is because it's rank 2, the third column can be written as a linear combination of the first two columns. But that doesn't mean that all three freedoms go away, because there is a freedom in choosing the scale factor of the addition of the two columns. So 7, 8, any other vote? 9 we have eliminated, and now we have an argument for 8 and an argument for 7. Yeah, so really think about this. The one freedom is restricted because the scale factor does not matter, and another freedom is restricted because there is a rank restriction. The rank is less by 1. So which means when I'm writing the third column, if I write the first term and I write the second term, I can't independently write the third term because I have to choose the third term such that the rank restriction applies. Okay, so there is a rank restriction of 1 from 3 to 2, and so there is also loss of 1 freedom. So there are 7 independent terms in F, really. Okay, which means if you give me okay, let's come to that. Okay, so here are the two the two matrices which are I didn't want to use the word essential or fundamental, so which are critical for the stereo problem. I put them like side by side, right? So essential matrix, it satisfies the equation PR transpose EPL is equal to 0, and correspondingly fundamental matrix, it satisfies the equation PR bar transpose, which is pixel coordinates PR bar transpose FPR PL bar is equal to 0. And essential matrix is of rank 2, and fundamental matrix is also of rank 2, and essential matrix encodes information on extrinsic parameters, but fundamental matrix encodes information on both extrinsic and intrinsic parameters. Okay, what's the relationship between the fundamental and essential matrices? Well, these and these are related by this relationship which we derived. Okay, all right. Okay, so now let's come to computing the fundamental matrix. Okay, so we'll see if I'm given two images, how will I compute the fundamental matrix? So we can compute F directly from the images. Well, I could have computed F if the cameras were completely calibrated, because if the cameras were completely calibrated, I would take the R and the T of the second camera, put the first camera in the canonical frame, take the R and the T of the second camera, construct E from it, and then take the intrinsic parameters of the camera and use those to convert E into F. But I'm saying I really don't need that. I can directly compute F even though the camera is not calibrated. Okay, and let's see how I can do that. If I'm given n corresponding points between the two images, so I have image 1 and image 2, and I say this point is the same as that point, and this point is the same as that point, and so on. I have some correspondences available. In the same way, so these are not point to line correspondences, I have some point to point correspondences available. In the same way as you had point to point correspondences available to estimate a homography, so you were able to do that. You did a least square solution for homography. So let's see, if I have some point to point correspondences available, what can I do? How can I compute F? Okay, so if I have n correspondences available between image pairs, but I have then constraint between those correspondences, then I would know a PR and a PL pair and a PR and a PL pair, so I can try to solve for the unknown F, right? Because there is a linear constraint here on F. It's a linear equation, right? It's like a line equation. Agreed? So here's a question. Every correspondence will give me how many equations? 2, 2, sorry? I mean, expand this out. How many equations is this? What's the size of this? 3 by 1. What's the size of this? 3 by 3. What's the size of this with the transpose? 1 by 3. So the whole thing is a 1 by 1, right? Which, well, so there's only one equation here. Let me write that just so that we are clear, right? X, Y, 1 times something A, B, C, D, E, F, G, H, I, except there is a constraint that it's a rank 2 matrix, times x prime y prime 1 equal to 0. Okay, so I multiply these two together. What do I get? I get A x prime plus B y prime plus C. I get dx prime plus ey prime plus f, and I get gx prime plus h y prime plus 1, this thing multiplied by xy1, right? Which is what? Well, this whole thing, ax prime plus by prime plus c times x plus dx prime plus ey prime plus f times y plus gx prime plus hy prime plus 1 times 1, which is just that, equal to 0. That's just like one linear equation. So every pair, like in the case of homography, every pair of points that you get actually give you two equations. In this case, every pair of points that you get actually gives you one equation. And actually, that's not accidental. Think about that. In a homography, that is precisely why we are able to do a point-to-point correspondence. Because from every point, we get two equations, which means we get a lock along this direction and a lock along that direction also. But here we get only one equation, which means like one direction is locked, the second one is not. There's a linear constraint that you get, which means you get a line, a point-to-line mapping. All right? So every correspondence gives me, let me fill in the blank here, every correspondence point gives me one equation. So which means how many correspondences have to be known for me to solve for f? At least 8. तो कितनी चाहिए? 7. Because the degrees of freedom are 7. Right? So if the degrees of freedom are 7, there are 7 independent terms, so I need 7 equations to solve this. Okay? Everyone understands that? Now that's actually true. I need 7 independent correspondences to be able to solve for this. But there is a caveat here. When I write those 7 correspondences and then I have a least square solution later, I'll build a least square solution to solve this. That's not an unconstrained solution that I can do. Within my solution, I'll have to embed some mathematics that will ensure that the result I get is rank 2, because it was only after imposition of that rank 2 that I actually got that I got 7 parameters, right? So it is not going to be a simple unconstrained optimization problem like what we have done before. I'll say this is my least square solution, but I have to solve this subject to the constraint that rank must be 2. Okay, and that's a bit more complicated mathematically than doing a normal least square solution that we have been doing. So actually for this problem, there is an algorithm which is called the 7-point algorithm, which needs only 7 correspondences minimum. And there is another algorithm which is called the 8-point algorithm. The 7-point algorithm uses precise rank 2 constraint, but it's a bit more complicated mathematically. The 8-point algorithm does not use the precise rank 2 constraint. It uses just finds the least square solution without imposing the rank 2 constraint. It imposes actually the rank 2 constraint later in the process. But it's very simple. It's about as simple as your previous least square solutions. Okay. So we will only cover the 8-point algorithm because it's simpler. Okay. So let's look at the 8-point algorithm. Okay. This is the algorithm now to compute the fundamental matrix. What is the input here? The input is a set of points in the left image and the right image, and this is what my constraint is. Okay. So where are my unknowns? These are all my unknowns, and these things will be known. Okay, this and this will be the known values. I'll have a correspondence between them. Okay, so what do we do typically? We separate out the unknowns into a column, and we write the known values as a coefficient matrix. That's the way to do least square solutions. We have done a lot of those before. So so actually this is what it comes out to be. Okay, you can try multiplying this out and see the coefficient with every f. So with this f, for example, I'll get plx bar and prx bar. That will come with f1, so that's what's here. And similarly, all the other terms. Is that clear? It's just matrix multiplication, nothing else. Okay, so which means what? This is this f is how would I solve for this f? It's a null vector of the matrix that will be formed here by these correspondences. Okay, so the 8-point algorithm is so the whole matrix is this. I'm given n point correspondences where n must be greater than or equal to 8 for the 8-point algorithm, and I construct a system Ax is equal to 0 where each row of A is a n by 9 matrix. Sorry, each row, no, A is an n by 9 matrix. Okay, I should just cut each where A is an n by 9 matrix with its rows as each row is this. Okay, I should put a subscript 1, 1, 1 for the first row and then 2 for the second row and so on. So I'm given 8. Because if I'm given 8 of those, then the null space is one dimensional, which is my solution. Yeah. Yeah, it should exist. Why should it exist? No, 9, 10, 100, 200, 1000, the null vector should still exist because the system is of Ax is equal to 0 form. So X is the null vector of A. So as long as you know that Ax will indeed come out to be 0, then X is a null vector of A. So the null space is at least one dimensional. Right? Okay, is that clear? Okay, so what we do is we first construct this A matrix, which is an n by 9 matrix, from the point correspondences. I just have to take my point correspondences, arrange them like this into an n by 9 matrix. Okay, and then now what I'm going to do next? Yes, because I want to find the null vector, so I can do SVD on A. So I'll compute SVD of A, which will be U D V transpose. Okay, and then because I want the right null vector, I will take the components of the column of V or the row of V transpose that corresponds to the least singular value of A. Right? I say least because it will not perfectly come out to be 0 because these are point correspondences, so it's image data, it has noise in it, but whichever is the least singular value, I'll say that column of V is my matrix, I mean my vector F, and then I will rearrange that into the matrix to get the 3. Now this is fine, this is good, except I have not imposed the constraint on this that F indeed should be rank 2. Okay, so what I can do, it's a bit of a hack, it's not a fully sound mathematical argument, but what I can do, I did this for simplification because imposing the rank constraint within the optimization was harder. Okay, within the solution was harder. So what I did is I found the solution, but the problem is this F matrix may not have exactly rank 2. If all the data was perfect with 0 noise, then indeed it should have rank 2 even if I solve it this way. If the data is perfect and the solution is perfect, it should come out to be rank 2. But now your data is imperfect. It has some noise in it, surely. And then you have solved it like this. So there should be some noise in F, and that means F may not have perfectly rank 2. So if you do this and find rank of F, you'll find that it doesn't have rank 2. So this algorithm, the 8-point algorithm, is a bit hacky. It finds the solution and then it like forces rank 2 on top of it. Okay, and how can I force rank 2? Now I have an F. How can I force rank 2 on it? Well, I take F and I do SVD on it. and I find out that all three singular values are there, but one of them is smaller than the other two, which should really have been 0. It's small because of noise. So what I do is I do SVD, force that smallest value to 0, I replace it with 0, and compose it back up. It's like you do an operation, take out the bad part, and then put it back together, right? So we decomposed it. We made the last singular value 0. So that's what d prime is, and then I compose it back up. Okay, so I compute f prime as u d prime v transpose, where u and v here are the same as what came from the decomposition of f, but d prime is just has definitely one value as 0, the smallest singular value as 0. Okay, it's a bit of a hack, because would I get like a really good f this way, because I really found a solution without caring about the rank 2 constraint, and then I just hammered a rank 2 constraint on top of it. Okay, actually, for quite a while in the computer vision community, people thought that this algorithm is not good, and in fact, the results you got from this algorithm were worse off than the 7-point algorithm. So the 7-point algorithm was nonlinear, it was iterative, it doesn't give a solution in one step like this algorithm does, but it always it could yield a more stable solution than this simple algorithm. So there was kind of like the dominant view was that this algorithm is not very good, till I think in 1999 Richard Hartley, he wrote a paper which was titled "In Defense of the 8-Point Algorithm," and he showed that with some appropriate normalization, this algorithm can perform as well as the other best techniques. So it's actually not that bad, and people do use it now, as they do use it in practical cases. Okay, all right. So here's an example, fundamental matrix example. This is code for the for creating the fundamental matrix. I didn't write code for computing A, okay, but you know how to compute A. That was the line, the row that I gave. So you have to compose those rows together, and then you do SVD. You get USV, and then you say, because MATLAB already gives you singular values sorted by size. I mean, the largest singular value is the first row, and then the next one, and then the next one. So F is really the last column of V. Okay, so end is a identifier in MATLAB that you can use just to get the last of that dimension. Okay, so because singular values are sorted, so I'm just, the smallest singular value is the last value, so I'm picking the last column of V as F, and then I'm reshaping it. MATLAB has a reshape function, you don't have to worry about that. I'm reshaping it into a 3x3 matrix. This is done in the proper way here, and then I'm doing another SVD on that 3x3 F, okay, to find UF, DF, and BF, and then the last singular value in DF, I force that to 0 because it was in general not 0. So I force that to 0, and then I recompute F from UF, DF, VF transpose. Okay, and now this DF is like, it has the rank 2 constraint imposed on it. So it's pretty simple code, a few lines, and you have an estimate of the fundamental matrix. Okay. All right. So this process is applied here. This is like a lab. You notice that they have put these markers at a lot of places, right? These sheets of paper which have some symbol drawn on them, and those markers are done so that correspondence is easy to find. Okay, so they have so this marker, for example, corresponds to this marker, so you can find their correspondence, and from those correspondence then he ran exactly this code and he got this as the fundamental matrix. Okay, and now one last comment that I'm going to make on this fundamental matrix is that in practice, I mentioned this Richard Hartley's paper in defense of the 8-point algorithm. People found out that this 8-point algorithm was not performing as well as the 7-point algorithm or some of the other techniques that people were using. And then Hartley showed in this paper that actually really is, there is a quick fix to the 8-point algorithm if you normalize the image points, image coordinates, so that so that they are not like 0, 100, 200 and so on. They are between -1 and 1. They are normalized so that their average value is 0 and their average length of those vectors is 1. Okay, so he showed that if you normalize that, the 8-point algorithm actually becomes as well as some of the other things. And the reason for that really is that if you have, one of the reasons for that is if you have really large numbers like pixel coordinate 100, 100, and you are multiplying those coordinates together so they are getting squared, so you get some very large values in the solution, I mean in that matrix, and some very small values in that matrix. Okay, and so this becomes the estimate here of the null vector becomes like numerically unstable. The large numbers really overpower the small numbers, and so he said if you do this correction, then actually it is a very robust algorithm. That's what he showed in this paper. Okay, so how would you do this correction? That's just a translation and a scaling in 2D, right? You can find the average vector, the average value of your pixel correspondences in the left image and the right image separately, and then subtract that from every coordinate, every pixel coordinate, so the average becomes 0. And then you can find the norm of all those vectors on average and just divide by that norm. So then the norm becomes 1. Okay, so then the pixel coordinates are in some other space, which is not, I mean, these will be like decimal numbers now. They will not be those integer pixel coordinates. But you use this pixel coordinate and this pixel coordinate, normalize both of them, and find f from them. And then you do a correction later, and then that becomes a much more robust algorithm. It gives you excellent results. Okay, all right. Any questions? So what we are saying is, given two pictures like this, you can directly compute, if you find enough correspondences, you can directly compute f, which encodes the whole epipolar relationship. Okay. One more thing that you can do is you can actually compute the epipoles also from f. Now that you know f, if I want to compute the left epipole, which is EL, now every epipolar line passes through EL. Okay, so you pick any PR. For every PR, this relationship should hold, right? Because that PR will generate some epipolar line, and that epipolar line does pass through epipole. So epipole is one of the corresponding points on that line, right? So which means PR bar transpose F EL must be 0. Okay, agreed? Is that the argument clear? Because every epipolar line passes through that, I could have picked any point on that line PL, and then this relationship would have been true. But EL is one of the points on the line, so in particular this relationship is also true. Right? Now if this is true, then what does that tell me? Either FEL is orthogonal to PR, right? Because PR transpose FEL is 0. So either FEL is orthogonal to PR or FEL is 0. Those are the only two possibilities that I have. Okay. And now my claim is that FEL can't be orthogonal to PR. Why? Well, because this relationship holds for every PR. If it's orthogonal to one, it won't be orthogonal to other because they are in the same geometry, right? So since this relationship holds for all PR, that means the only possibility is that FEL is 0. And if FEL is 0, then EL is the null vector, the right null vector of F. Okay, so that's like really neat. I have F. I can just find the epipole very simply by finding the null vector of F. Yeah, and there should exist definitely a null vector because F has a rank deficiency. So that's what the null vector is specifying for you. Yes. I'm saying because if there was one particular PR that I chose, then yes, there could be something orthogonal to that which is 0. It's a 2 space, right? I'm talking about a 2 space. So there is a point PR in that space, which is this vector. So yes, I can get, for this one, I can get one orthogonal vector and then this relationship could hold. But I can't get an orthogonal vector which is orthogonal to every PR. That can't be true in a 2 space, right? And therefore FEL itself must be 0. That's the only way this equation can be true for all PR. And if that's true, then FEL must be 0. So EL is the left null vector, the right null vector of F. And similarly, ER is nothing but the left null vector of F or the or the right null vector of F transpose. Okay. So I can just find the left epipole and the right epipole. They are actually embedded within F. I can just find the null vector, the right and the left null vectors of F, to find the epipole. Just do SVD of F or F transpose depending on which epipole you want, and find the column of V's corresponding to the least, corresponding to the 0 singular value. Okay. Yeah. Yes. Yes. Yeah. In fact, we don't use PR to compute the epipole. We just use F. Right. So there's no in computing the epipole there is no need to pick a PR. Okay. One last thing that I want to quickly mention before we wrap up this discussion on stereo. We talked about rectification. We said that the case where the camera just only translates, the epipolar lines will be aligned along the scan lines and they'll correspond to rows. Now other cases, the epipolar lines might converge, they might meet in the middle of the image and so on. But that case can be rectified into this particular case. So let me just give you kind of like a simple relationship there. I won't derive the whole thing. But given a pair of stereo images, the intrinsic parameters of each camera and the extrinsic parameters R and T of camera 2 with respect to camera 1. Yeah. So that's my R and T of how the camera 2 is rotated or translated with respect to camera 1. Then I can compute the image transformation, which is actually a homography. It turns out that it's a homography. I can compute the image transformation that makes the epipolar lines collinear and parallel to the horizontal axis. Okay, so given these solid lined frames, given the original cameras are like this, the ones shown in black, but I can transform this into some camera image, into some homography, and I showed you an example of this yesterday, where the epipolar lines will be scanned. And that transformation is just some H1 applied to this camera and some H2 applied to this camera actually. Okay, and we can actually find that. The steps for doing that is, what we do is we first rotate this camera so that the epipole goes to infinity. Okay, and how can I do that? It surely is a pure rotation, so it's a conjugate rotation homography, which is a K inverse type of homography. Okay, because it's a pure rotation of the camera. So I can try to find that conjugate rotation homography which maps my epipole to 1, 0, 0. So I know what my epipole is. Okay, I know what my epipole is, which is, let's say, EX, EY1. Okay, so I try to find the homography, which I know is a conjugate rotation homography. So I know K inverse, so it's really just R. I'm trying to rotate such that this maps to 1, 0, 0. Okay, because 1, 0, 0 is the point at infinity along the x-axis. And now with this relationship, actually, it's not difficult to find H. It's actually not a unique H. There are a bunch. I mean, it's not just that only one H will do this. There are a bunch of solutions for H that you can find. Okay, so first you rotate the left camera so that your epipole goes to infinity. You try to figure out that rotation and set up that conjugate rotation homography. Now you apply the same homography to the right camera just so that the original geometry is recovered. Okay, and now in that geometry, you know that the other camera is rotated by R with respect to the first camera, so you rotate that by R, which means you do another conjugate rotation homography where R is known. What is this R? This is the extrinsic parameter of that camera. And now they are both parallel. Now you adjust their scale so that the same line maps to the same row. Okay, that's a hand-waving way. I've not written the equations here, but I've just shown so that you get some sense of how rectification is done. This algorithm, I think, is by Zhang. There are a bunch of different rectification algorithms, and this one is by Zhang, I think. Yeah. Yes, that's true, but it will happen after I do the actual rotation of the camera. First, okay, so first I rotated this camera, okay, so that the epipole came to infinity. So this was like this. So I rotated this camera, but I said, okay, let me rotate the whole thing so that the relative geometry remains the same. Okay, and now if the relative geometry is the same and this one is rectified, then this is just a rotation of R. I already know that rotation, so I will do that. If I just applied rotation on R on this will not be rectified because well, this camera was not in the rectified view to begin with. So when I rectify this, I do both together, so they are in the same geometry, and then I rotate this by the actual rotation of that camera. And now this because this is rectified, this is now in the same rotation, so it should also be rectified. And then I adjust their scale. Okay. All right, so this is a slide I had used earlier at the beginning when I started talking about the essential and fundamental matrix, but I really didn't know at that time what they are. So I'm just going through this slide again. What do? We first find a few corresponding points between the images. How we do that? That's next module. We'll talk about image correspondence. Okay, but we first find a few corresponding points. Then we estimate the fundamental matrix from that. Then if the camera calibration parameters are known, I can actually compute the essential matrix from it if I want to. Okay, now I rectify the images to align to the scan lines using the process I described on the previous slide. Now my epipolar lines are scanned. This is a pure translation case now. Okay, so I pick a point here, I correlate here to find where's the best match, and I get a disparity map really. And that disparity map is inversely proportional to depth. Now if I really want to compute depth from it, I have to do this ray intersection from those points, which actually requires camera parameters. I'm skipping the mechanics of that part, but I've already kind of given you the argument that we need to do that. So if you really want depth, if you're okay with the disparity map, you can just stop at the second last tab. But if you really want depth in meters and so on, you have to have camera extrinsic parameters available to be able to cast those rays and do triangulation. Okay, that process, I've actually given you the equation of that, so really I've not missed it, right? Remember that equation, Z is equal to FB over X2 minus X1. So X2 minus X1 is that disparity, so you need to know F to convert that into a Z. You need to know F and you need to know B. B really is that translation between the cameras, the baseline. Okay. All right. The last thing that I want to mention, and I'm stating these actually without proof, just so that you know these facts. If the camera calibration parameters are fully known, then complete 3D reconstruction is possible. If only the intrinsic parameters are known, then reconstruction is possible only up to a scale factor. I wouldn't know the lengths in actual meters, but I would get the correct structure. But it can be a similarity transform of that structure. The actual structure will be a similarity transform of that structure. And if no calibration parameters are known, you can still actually do reconstruction, but that reconstruction will be up to a 3D projective transformation of the actual structure, which means you can get a reconstruction like this, shown in this figure, right? If you know no camera calibration parameters, you might reconstruct this hut like this. It's a 3D projective transform of the actual structure. This is a fundamental theorem in stereo. I'm not discussing that. I'm not proving it. I just stated the result out of that theorem. Okay. So bottom line, if you want to get real world measurements constructed properly, both your cameras should be calibrated. You should know the K1, K2, R, and T of the second camera with respect to the first one. All right. All right, that's all I wanted to talk about stereo in this course. Any questions? Okay, yeah, question? No, okay. So the next topic that I want to discuss, stereo is reconstruction of structure when you're given two images. Okay, but what if you had a lot of images, not just two? Okay, so there is actually a formulation of stereo which is called multi-view stereo, which uses all the constraints from those images to do that. But then there are other formulations also which are different from stereo, and one of them, which is very interesting, is called structure for motion. Okay, and the idea for that is this. So if I have a video, now this video is really a lot of images of that structure. Okay, so it's any two of them could have been stereo, but it's not that I have two images. I have like 100 images or 1,000 images of this structure. Okay, so what is possible is that I can use that to compute to compute the point cloud, which means the 3D of every point, and also the camera location. Okay, because what happens is that if you notice in that video, so you see here those pyramids are actually a location of cameras, and this point cloud is actually the structure, and you can't really tell how good this point cloud is, but if you texture map it, you can. So now we're going to show this with the texture map. So that's the point cloud with a texture map. Okay, now if you move the camera on this graphical rendering of the texture map, you see that the structure has been recovered, uh, I mean, fairly accurately. Okay, it's a pretty good reconstruction of the structure, and in fact, if you texture map it, not just show this shaded, if you texture map it and move the camera around, you see that it looks pretty nice. Okay, these are synthetic views now that we are showing you, but it looks pretty nice. Okay, so if I play this again, the first part of this, where is the information of structure? The information of structure is really in the motion of these points, right? If you look at one point, let's say the tip of the nose is moving in this video, and it's moving differently from the eyes and from other points which are at a different depth. Okay, that's why we call this structure from motion. If I am able to measure the motion of every point, I should somehow be able to convert it into texture, into depth information, into the 3D coordinates. Okay, if I move the corners of this laptop move differently than those chairs. Okay, so if I had a video going like this, and I track these points, the corner of these laptops, I track these points in all the frames of the video, and then I track some point on that chair in all the frames of the video. Then from that information, just the tracking of those points, just the motion of that points, I should be able to somehow convert it into structure. That's the idea of structure from motion algorithms. Now, what I'm going to cover in this is what we call the rigid structure from motion. Rigid structure from motion is that the actual object is not moving. The actual object is stationary. So that means that any motion in the image that I see has been induced because the camera was moving. Okay, but there is also a problem in vision which is called the non-rigid structure for motion. What if the camera was moving also, and while the camera is moving and taking these images, the object itself is deforming, like a walking person or so on. So that's called non-rigid structure for motion, and that's actually a much harder problem than the rigid structure for problem, because this problem is well constrained. There are enough constraints to compute those points, but the non-rigid structure for motion problem in general is under constraint. You don't have enough constraints compared to the freedoms of the solution. Okay, just so that you know, our vision group here at LUMS has some important contributions. The PhD students who worked here, they have some important contributions to the non-rigid structure for motion problem, which has advanced the state of the art on this problem significantly. But that was a few years ago. Just very recently, last year, some very robust solutions were proposed based on deep learning, actually, that solves this problem well. But otherwise, this problem is under constraint and difficult to solve. That's the non-rigid part. But the rigid part that we are going to discuss is well constrained and has some very stable solutions. All right, we'll stop here. We are out of time. Any questions? Okay, so remember I announced we'll have an additional lecture on Friday, so that we make up for the lecture we lost due to the additional day of Eid break, and we will also have a quiz on Thursday, which is on the camera models part. That I'll announce. I have to reserve the room, so roughly I think 10 o'clock or something. But I'll it depends on the room reservation. So as I find that, I'll post that on the portal and also on the WhatsApp group. Okay. All right. Thank you.